So in part 3, let's actually finish up, make a few comments about the very last example that we looked at. Hope this is visible. I took the parametric function that we had. I changed the variables from UV to ST, and I entered that information into the Wolfram Alpha free online 3D grapher, as you can see there. And if you look at the surface that we get there, here's the z-axis. You can see that it fails the vertical line test for a 3D plot. So this surface does not give z as a function of x and y, right? Because if it did, it would pass the vertical line test there. And I suspected that that was the case once I reflected a little bit on the equation of the tangent plane that we got. The tangent plane, recall from notes at the end last time, was x plus 2y equals 0. Well, so if you didn't know you were in 3 dimensions, this is a line in the xy plane, right? And where I do have a ruler that helps me graph. There we go. So then you can actually get a fairly good sketch of the tangent plane just by realizing, okay, so x and y, when x, so this is just y equals minus 1/2 x, right? So line like that, and then the tangent plane here that we got is this vertical plane. So the surface, it makes sense that that surface, is just touching this tangent plane at some point. Actually, the point was down here on the line, right? It was some right over here, something like this. So the surface is just touching this tangent plane at a point and is not, and if that's the case, which it would appear to be the case, then the surface that we were working with given by R is not does not determine S as a function of X and Y. I say all of that because we're now going to discuss the special case of this material. Special case S is given by Z equals f of xy. So in other words, S is all of the XYZ points where Z is f of xy. And when we have this special case, actually I may turn my computer off here. When we have this special case, we can take X and Y to be the parameters. Of a vector function. So then what we work with then is R of xy xi. So x is determining where we are along the x-axis with, so the I standard basis vector, yj plus f of xy k. All right, well now let's just walk through the material that I did in general in the last lecture. Let's do it for this special case. What is the partial of r with respect to x? So that would be, let's switch notation for some reason. That would be 1, partial of y with respect to x is 0, and then f sub x, whatever that is. R sub y is 0, 1, partial of f with respect to y. And then we can also do this cross product in general. R sub x cross R sub y. And we've got it lined up here. Let's just, go through what we have here. Your I component is this product minus this product. So that's just minus f sub x. So minus f sub x I. Your y component is minus this product minus that product. So with the middle column deleted, this product minus that product. So minus f sub y. And then your k, so times j. And then your k is this product minus that. So that's plus k. And that's your normal vector. You could also write the normal vector in this bracket notation. And so then at a given point, x0, y0, your normal vector is minus f sub x at x0, y0 minus f sub y at x0, y0, comma 1. So that's our normal vector for the tangent plane. Any point P of xyz in the tangent plane then it must be the case that this normal vector, let's go over here, I'll suppress the point now, minus f sub x minus f sub y 1 dot x minus x0 y minus y0 z minus, and z0 would be f of x0 y0. So this is the old dot product here. So I'm kind of bringing out at the very end here, for the point x0, y0, f of x0, y0. For this point on the surface, and then any point in the plane, this dot product here must equal 0. So then if we multiply this out, minus f sub x times x minus x0 minus f sub y times y minus y0 plus z minus f x0 y0. All of that equals 0. Then you can solve this for z, and we get our old formula for a tangent plane. Z equals f of x0 y0 plus f sub x at x0 y0 times x minus x0 plus f sub y at x0 y0 times y minus y0. So what we already knew, but now a new derivation of this old fact. So I apologize. I'm having brain scatter moments this morning. I didn't really, should have stated this earlier, that the context we're in here is, a specific point that's on the function, and then any arbitrary point that's on the tangent plane determined by this surface. And it's just a new derivation of the old formula. Let me see. So let's actually take a break at this point here, and we'll come back, and we need to start looking at surface area and how we compute surface areas, especially for surfaces that are not necessarily functions of x and y. So actually the material that we see from here on is kind of going to have two versions frequently. It'll have the general version in terms of general parameters u and v, and that general story will hold for surfaces that are not necessarily functions of x and y. And then there's the special case, like we did this. So this sort of making a special case, you're going to see that over and over. It's nice because it reinforces the general case, and it also is kind of a nice simplification that you see a lot in a lot of problems. Okay.